Hello, everyone. And it's my pleasure to give another tutorial on controlling your MFA using Python today. So actually, we have received some very useful feedback from the same session last year. And we have heard that many of you said, I want to know more. And with that, actually, I decided to make a new session this year just to cover more details and make sure even if let's say you're very new to the Python program, you should also be able to follow this routine and then try to program everything from the beginning. All right, let's quickly start from the Zoom. And let me start from screen sharing. Good. So we are now here. And then I will switch to my PowerPoint slide, which locates in a PDF format. So let's see actually what we should get prepared ready before running any kind of measurement using Python or more specifically on Jupyter Notebook. So what you will see here actually is, actually we would really need to install the latest LabOne software. This part actually is important. I mean, some customers or users decide to ignore it, but there could be a problem. Remember, when we use this kind of automatic upgrade or installation of Python program or Python API using pip install commands, if you do that, this command will always update to the latest version. But in case your MFIA was shipped a few years ago, then the built-in software might be old. This could lead to a version mismatch problem, and occasionally there could be bugs. And therefore, I think it's simpler and far more straightforward if we keep everything up to date and just use this latest version of both LabOne and the LabOne APIs. And as you can see, I also listed a few useful learning resources, including the video from last year and also the programming menus and some examples. Well, they are too detailed. We don't have to look at them for now. And I would only recommend to look at them later when we have more specific questions in mind. There are also a few tips that I would like to share with you today. And actually, I shared the same tip also last year, but I think it's worth repeating them. For beginners of Python API to our instrument, I would strongly recommend that we follow the graphical user interface, the GUI, as a reference. This is because most of the features we have already programmed in the GUI, and using the GUI, most times it saves lots of effort, and you don't have to really reinvent the wheel. More importantly, for Python user and also for MATLAB users, you can also try to utilize the API command log. I will show you next how this works out. Almost, maybe let's say 95% of the commands which we perform in the GUI can be copied and pasted into your Jupyter Notebook and just run as it is. And next, there are also some additional tips which we will see next. For example, if you want to program the Python controlling the DLTS, both the MFI and your Lakeshore or whatever temperature controller, I would recommend that we program separately or independently from each other. And then, we can optimize one after another. This actually makes things clear and more structured. So the setup today actually looks like this. I think if you are familiar with DLTS, or maybe if you have discussed with myself or some of my colleagues before, probably you should be quite familiar with this kind of setup. It's actually quite simple. We only need a very short BNC wire to connect the auxiliary output to the auxiliary input. And the device under test in this case is just a small LED as a DUT, which is mounted on this MFITF test carrier. In this setup, what we want to resolve is a very small transient, somehow excited by square pulse. And to do that, we will need to use a few different modules. This includes the threshold unit, which can be used as a function generator here. We could also optionally use the scope for monitoring, but due to time limitation, we will skip it for now. And probably we will also need to use the sweeper module to run some CV or CF to find the optimized parameters. And finally, using the plotter or DAQ module to get the data. So let's finally get into the program today. Actually, there's one more slide. I really want to emphasize it again before we moving deeper. there is something important which actually I skipped last year, but I think really worth highlighting, which is this API structure. As you can see here, looking from the top to the bottom, we have different API sessions. For example, Python, ZDA Python API locates in parallel with the web browser. In this case, the GUI locates in the browser. But differently happen afterwards is the GUI or the LabOne connects to the web server first and then goes to the data server. Whereas in the case of Python API, it goes to the data server directly. The consequence of this is if something only exists in the web server, then the ZDA Python API would have no access to it. This is the case for the plotter. So in other words, there's no plotter in the API. And likewise, maybe some of the users, they ask, I like to use your API, and also I like how your GUI looks like. Can I take the data from API and plot it in the LabOne GUI? Well, in short answer, this is also not possible because they don't talk to each other, right? They talk to the data server, but they are not wired directly. And to put it in another way, things which actually locates on the data server, these are common instrument settings, they are shared. But when we talk about modules, plotter or sweepers, the sweeper on the web server is a different sweeper from the sweeper on the ZDA API, so they don't know each other. And another thing actually we should talk about is here at the bottom of this chart about the data server. Well, this is only important or relevant for DLTS measurement, I would say. You see, the default way of opening MFIA is always at a local network address, something like 192 or maybe 10 point something if you connect with Ethernet. But for DLTS, we might want a faster data rate. And for this, we want to set the data server to run locally on the PC. A local PC in this case becomes this 127 address. And to do that, we actually need to switch to the GUI first. So let's see how it's done. This is the GUI when you open the interface. And in this case, I'm in the company, so you see multiple instruments connected. Some of them are in this 192 address, some are in 10 address. So to change to the local data server, you switch to here. And then you will have this local data server ready. Once I click it, you will just see a freshly opened LabOne GUI popped up. That's it. And if you are curious what happens afterwards, we click this API command log, then we just see what is needed to build a connection to the instrument. For this simple demo, actually, we only need these 3 lines. Actually, 2 of them are good enough. Import time is not important. We need to copy and paste them into our Jupyter notebook, which I have already done here, and just run it. Then the instrument will just be connected. But I guess maybe some of you might have a question. How should I verify that the instrument is connected by the API? There's no feedback so far. Well, good call. For that, actually, we need to move to the next demonstration about plotter or plotter-like function. So let me emphasize again, there's no plotter in the API, but there are functions that can achieve similar features or functions. Well, depending on your use, this can be set and get, which actually somehow can fetch the data at very long time interval, or poll and subscribe, which is more suitable for reading data at a faster rate. For the most basic one, we can start with this set and get. So how it works is actually quite simple. For example, the default program here shows 1 kilohertz. And in case maybe I want to change it from 1K to 10K, I add a 10 here. And you can see the latest command at the bottom of the screen. And if I refresh this API command log, the bottom line here also shows what has been changed. If I copy and paste this into my Jupyter notebook, I should just be able to change the frequency from 1K to 10K. But if I do complete the same, there will be no change, right? Because both are setting their frequency to the same value, 10K. So how about let's change to 1 megahertz, 1 million here. If I run it, let's go back to the graphical interface again. You see the frequency is indeed updated to 1 megahertz. And again, remember, the reason why it's updated is because these are common instrument settings, and they are shared between the API and the graphical user interface. Likewise, if you set some value here and forgot how much it is, and to read the data is also very simple. So what is opposite to set? get, right? So we use this DAQ.get to get the value, which in this case is exactly 1 megahertz, as we just said before. So at this point, I guess some of you, if you are familiar with Python, you probably can already figure out what I'm trying to do here. So with these 3 lines of code, or actually I don't really need the very last line, so 4 lines. With these short codes, I'm already, let's say, programming a sweeper using this simple command. How it works is very simple, right? This NumPy linear space simply generates a arithmetic sequence. So the first argument is the starting value. The second is the last value. And the third argument is the number of steps. So in this case, it will generate a sequence from 1 to 10 in a total of 10. That means 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If I run it with 1 second time interval, I should just be able to set the frequency from 1K to 2K up to 10K. Let's see how it looks like. If I click run, and then let's go back to the GUI, you will see indeed these frequencies updated 1 kilohertz per second interval. That's actually what we want, right? So as you can see, programming is very easy. At this point, you have already learned how to program your own sweeper. But there could be questions. Okay, if it's that easy, why shouldn't I just use this? And you have a dedicated sweeper program. Does it really help to have a program like this? Well, it does. Remember, with these 4 lines of code, we didn't actually set any optimization. There's no settling time, no averaging, nothing is included. I mean, in most cases, actually, it doesn't work out. And more importantly, actually, there's another reason why you shouldn't really use this kind of command when you try to read the data at very fast rate. As you can see, there's a sleep time of 1 second to define the interval. If I comment this out by adding this hashtag and run it again, you will see actually, at a certain point, it doesn't really work as expected, right? After 8K, it doesn't go to 9K. It actually repeats the same value. The reason is because the compilation of all these commands in Python API takes time, right? So there's a chance that while the previous command is also running, the second already starts. Then what happens is this command is just simply read twice. That's actually not what we want. But how should we resolve this problem? Well, very easy. We freeze the command and let the system start to run, right? So basically, put in another way, I will set the time or timer to start running as 0 seconds, and then define where to start our reading. That actually is defined or can be, let's say, achieved using this subscribe and poll command. So what is important here is to include this sync command. As I pointed to you before, the use of it is very simple. We only need to consider it as to define a starting point as t equals 0. And then we just define a duration of data we want to pull out using this poll command, and then read the data as we want. So if we see how it looks like here, let's go back again using this subscribe and poll. By the way, the path here is under impedance and \sample. It's very similar as here. I just change frequency to sample. That sample gives the result. I hope you can also figure it out by yourself. If not, just have a look at the command log or the user manual. They will tell you which commands or which node tree should look like. So if I run this command within 0.1 seconds, as I defined here, very short time frame, we should just be able to get the data. But at this point, I guess some of you might have already questioned. This is not the plotter I get in the graphical user interface, right? The GUI actually gives me something like this. In the plotter tab, what you will see is, for example, I get maybe just I get some impedance value. In this case, let me just remove all the other duplicates. So in this case, if I have some resistance value, let me add it here from the enabled impedance, and under this one, I guess that's the impedance we want. And let's try to set it from here. Okay, where's my data? Okay, so this is actually from another instrument, but actually you could already see some results from here, right? So what happens here is it actually shows the result at a very fast data rate, but whether it makes sense or not, it gives you a continuous stream of the data. But here, using the API, what we see is just the numbers, numerical values. Well, there's a step in between, which is data processing and plotting. But for that, actually, we need to look at the slides again. So there are a few tricks that we should learn here. So the first thing is the data actually looks like a layered structure. So we can somehow call the data using this time step as the key to read what's inside. And if we see another bracket, square bracket, then we have another layer of key to get it out. This is called nested dictionary. But at the moment, actually, we only need this single layer set to read the impedance value. But apart from that, I guess we might also see the impedance data, how it looks like. It actually looks in Cartesian format, not in polar units, right? So it means we can get real and imaginary impedance, but not the absolute impedance. But to do that is also very simple, right? You only need to call numpy absolute, ABS. That's a single line of command. You convert everything into the absolute value. But there's another thing which we should take really some care of, which is time. Okay, there's a time here, but this is not the one we want to look at. What we want to look at is this one, the timestamp. You know, we human use seconds or minutes, hours, days to record time. The instrument has its own unit, which is the sampling clock. The sampling clock actually has, if I convert it in the real time, has a time step or time interval about 60 nanoseconds or inverse of 60 megasample per second, right? So to convert this timestamp into our human readable time format, I just need to divide it to this 60 megasample or multiply by this 16 nanoseconds. Well, that's actually a simple thing. But remember, what we want to do is we want to convert this entire array or entire series into a human readable time format. So what happens again is we will use this numpy linear space, which actually generates a arithmetic sequence. Remember, in the plotter, what we want to do is we start from time equals 0. The length is not important. We just call LEN to get the length. But the last data point here is not exactly 0.1 seconds due to some data granularity. So we have to really calculate it. That's actually quite simple, right? So we will use the last one minus the very first one in this array and divide it to the timestamp, or sorry, the sampling clock. If I run this will just convert this time step into real time. So as you can see, this array generates some data which really start from 0 seconds up to 0.00998 seconds. It's very close to 0.1 seconds, but not exactly 0.1 seconds. That's why I said we can't really rely on this 0.1, which we just write here. But regardless of that, we already get the time ready, right? This is the time that we want. And we also have the absolute Z ready. So this is the plot command with X as time, divide as this absolute Z. If I run it, I should just be able to have my plotter. So let's just wait for a second and let's see the plotter is running. So actually this gives the same plotter as we could see in the graphical interface between maybe whatever 0 seconds to 0.1 seconds with some absolute impedance value. So at this point, I hope everyone is or could be happy with this kind of a command, how to get the data and how to plot the data. And let's move forward to the next demonstration. In the next demonstration, actually, I would like to show you or share with you sweeper. The sweeper command actually works very similar to the other commands, but needs also some special attention. How it works like, okay, let's quite quickly review ourselves. Remember, actually, in this kind of settings, what we should do is, so we want to do some settings and we set up the sweeper. But the settings of the instrument, these are commonly shared, right? So let's quickly try to add some DC bias to it. For example, I will open an auxiliary tab. I try to give maybe 1.4 volts DC offset value to my device. And then I will change these setups a bit to maybe, let's say 100 millivolts. And then I will go to the lock-in tab, which actually locates here, which actually will tell the instrument to add on this 1.4 volts DC bias to the actual measurement. As you can see, what I'm doing here, the ranging step is already happening, and the voltage here already is added to 3 volts. And this green mark shows that I'm actually reaching something higher than the default, just 1 millivolts AC amplitude, right? So this is added. At this point, if you refresh this command log, you should actually see the setup from here until here is what exactly that we have done in the GUI. But we don't have to duplicate ourselves, right? The things is already existing there, and we don't have to run them again in the Python Jupyter notebook. But at this moment, if we go back to the sweeper, let's actually try to open a new sweeper by dragging it to here. And then just run a quick sweep. Let's see how it looks like. So the sweep actually will start by itself. And then after maybe just 1 or 2, actually 4 seconds, it will come somehow finish. So the default view is, again, the body plot. But for this specific case, body plot is very likely not so interesting. What is interesting actually is the expereiement mode, the Nyquist plot. But I will invite you again to watch the API command log update here, right? So the default settings here is plot 1. But if I change or click this expereiement mode, you actually would see no updates, right? So this is not changed. Plotting itself is a separate task. Plotting is not part of the API's job or the GUI's job. This is a totally different thing, right? So that's why if you really want to achieve this kind of plotting by API, we should also spend a bit of time to learn how to plot by ourselves. But anyhow, this actually gives a very nice Nyquist plot and RC semicircle of this small LED. If you want to achieve that, let's go back here again and refresh the command log. As you can see, starting from here, there's a green line telling that I have started a new sweeper. I can just copy and paste exactly the same commands from here to here. But what is important, actually, there are a few lines which is commented or marked in green. If you want to run this code, make sure to uncomment them, right? Otherwise, your code won't run. I have already done that before the talk so that we don't have to waste time here. If I run it, what you will see is exactly the same thing after maybe a few seconds. So initially it takes some time to initialize the setup, but after again, maybe about 4 seconds or so, the entire progress will reach 100%, and then all the data will be collected as what we saw before. So until now, actually, we have just called the sweeper to run the data. The data is ready and saved into this result variable. If I again run this result, let you see the data, now probably you see a more structured result, right? So there are really multiple layers of this square bracket. And really, if you really want to get maybe one of them, maybe the real part of the impedance, you need to look down. So after these 3 or 4 layers, there are another 2 layers. And deep in below, you have this absolute Z. And if I go even further, there are frequency, which you can try to call, but since I'm looking for imaginary Z, you see this is really called as imaginary Z. So if I really want to read it, you go up to here and see what is inside this real Z or the imaginary Z and try to run it again. And this array will be just the real Z or the imaginary Z that we are looking at. So again, plotting is a very simple thing. We only need to plot X, Y, right? So real Z versus minus imaginary Z. That is the Nyquist plot. I click run. This just gives the same RC semicircle that we just saw in the GUI. At this point, I guess maybe some of you are happy already, but probably some of you are not. Maybe you want to know how to save the data. Well, good question. I mean, if you are already familiar with Python, I don't have to answer this, right? So the data is there. You save the data into whatever CSV file or text file as you like. So this is very simple by using the numpy command. Alternatively, actually, some of the users want to save the data into the same format as we actually have in the GUI. These are the history tab. As you can see, we can save HDF files, maybe MATLAB files, or even ZView supported TXT files. If you want to do that, then we need to pay a bit attention. So let's go back here again. So as you can see, default command here actually use this result, and then there's no save command, but because this result equals sweeper.read cleans the buffer by itself automatically, right? If I want to save something, I should save it before the sweeper read command. That's the only thing we should know. But other than that, everything else remains the same. If you want to run it, just uncomment these two lines and maybe also define some file names or save directories you like, and then you will have the data ready. So that's how the sweeper works. And finally, we can move into the DAQ module. So the DAQ module actually shares similarities with both the plotter module and the sweeper module. With plotter, actually, it shares the same or similar thing on timestamp conversion. And with sweeper, it uses the same subscribe and poll command. But there are also things unique to it. But regardless of that, let's warm up self again, just to recap some brief knowledge. There are common instrument settings. For example, if you want to set this threshold unit to give a square pulse, if we want to do it from the graphical user interface, we don't have to repeat the same process in the API again. But the DAQ itself is independent, and that needs to be done separately in the API. So let's see how this can be done. Let's go back to the API first, the GUI first. That's where we were at the previous moment. So to set the DLTS up, it's actually quite simple and straightforward. We open this threshold unit, TU, set up, let's say, a pulse between maybe 6 milliseconds on state, 1 millisecond off state, and activate it. In the aux tab, I will try to give it maybe -2 volt, let's say, proportional gain, and I will also zero the DC offset, which I said earlier. Remember, the analog adder should be set on, but this I have already done in the previous setup. At this point, if we go back to the Impedance Analyzer tab, in the Advanced tab, we open it. We can set the measurement bandwidth to 100K, and maybe also the data transfer rate to 107K. That's the maximum we can reach on the instrument. At this point, if we go to the plotter, we only look at the capacitance, right? At this moment, if we keep zooming in, we could already see how the capacitance transient looks like with respect to time. So that's how you can do things with the plotter module. But if you want to get into DAQ, you only need a few extra steps. The difference here is, of course, we need to choose the impedance parameter to the capacitance as the parameter of interest, but we also need to go slightly into the settings, change it from the default values, because we need to tell the instrument to have a proper trigger. This is the difference between the DAQ and the sweeper module. Here, for example, I want to use a software trigger, so I will just use the impedance itself, REP parameter 2, the capacitance as my trigger, and I will use this to find the trigger level automatically. In the grid settings, I will set a repetition of maybe 10. And at this point, if I click single, you will already be able to see the data coming out in maybe a second, and it's already averaged out much cleaner than we are seeing before in the plotter module. It actually looks quite straightforward, and so far we spent only maybe 2 minutes or so to do everything in the GUI. And to do the same thing in the API is actually quite simple. Remember, again, if we refresh it and go to the end, we have these DAQ module related settings. We can copy and paste them again, and remember to uncomment this part to run it in the API. If I do that again, it may be just a seconds level, you can just get the data ready, stored in a variable called as result. If I print it out, you again see the nested addition structure. But now the difference comes, right? Here, it's not sample anymore. It's sample dot parameter 1 dot average, because we have already taken the impedance value parameter 1 and we have averaged it. And if you go slightly further, I can also tell you, rather than 2 zeros right after here, we put 1 in the front and 1 in the end. And this is because we designed this DAQ for reading 2D data. But anyhow, this is only a tiny difference. And if you are familiar with this kind of layered nested addition structure, this takes no additional time. At this point, I can just run this timestamp again and see or show you the new array of timestamps, basically time in machine readable format, but not human readable. Again, we can follow the same procedure to convert the timestamp into real time by using the NumPy linear space, right? Starting from 0, use the length as it is, and get the difference between the last to the first one and divide to the sampling clock of the instrument. the real time, if you see, we get here, start from really 0 seconds and ends something like, 4.8 milliseconds. Is the same as we have just seen in the graphical interface. Okay, so now actually we have this new time calculated, and the real time gives about 4.8 milliseconds. For plotting, actually, it's the same thing as we saw before, right? So again, we will just use plot x and y. X is just time, which we have already get from here. The y is the capacitance value, looks slightly differently from the sweeper or plotter because we have this already averaged parameter 1 in the front and the 0, 1 in the first, 1 in the end. Let's write again and see the result just comes out as it is. And at this stage, if we compare this result as what we have in the graphical interface, you will just see exactly the same thing. So that's how you do everything from the API. And that actually completes this part of the demonstration. And with that, we can move forward into the conclusion today. So to quickly summarize this part, you see, actually, I try to make 3 take-home messages that we should really focus at. So first thing is we have the common settings at the instrument level and also the module-specific settings, right? The common settings, as I did earlier in this sweeper tab, they actually looks pretty much the same in both the API and the GUI. We don't have to duplicate. Of course, you are welcome to program everything in the API, but they are all the same. Module settings is what we should pay attention on, right? The sweeper in the API is different from the sweeper in the GUI. They don't know each other. Also, I need to really clarify the difference between the API and the Python. The Python API actually only fetch the data. That's all it does. Plotting and data processing is part of Python itself, not part of the API. This is a different task. However, this doesn't really require too much knowledge, right? As you can see, what I did here today includes only 3 parts. The time-step conversion, which is only included in this kind of, let's say, NumPy linear space. The next dictionary requires only pull out data layer by layer. And finally, you only need to know plot x and y, right? This gives nearly all the programs or all the plots that we are being able to see in this graphical interface.